Okay, starting now. So if you had it up standing by, you should be hearing my voice now. So chime in, let me know you're hearing me. All right, looks good. Okay, so what I want to do tonight, I kind of rethought my expectations for lab number 2, and I think so labs will be smoother going forward. I should take some time to specifically go over lab number 1 and my approach to it, which expands on the requirements. So not everything I'm about to show you is something I expected you to do on lab number 1, but it's the kind of thing that I'm going to expect going forward. So what I'm going to do here is show you some stuff I've done. And so let me pop over here. One thing I did that I want all of you to do, and I'm just going to give you a copy of this that you can use, is creating a stopwatch class. If you've already read the sections of the textbook, you would have seen where he talks about writing a stopwatch class. This is different. This is not quite the same as what's in the book. Let me get the Discord window over here so people can kind of see what's being said. There, I think that'll work. All right. And I think I will adjust my virtual machine size a little bit so that I can keep that Discord chat visible. I really should set up a... I don't know if any of you do streaming, but there's a way I could set this up so that I could have the Discord on a different screen and still have it visible in the stream, but I haven't done that. Uh-oh. Oh, please no. Okay, there. My virtual machine decided it was going to hang momentarily. All right. So what you're seeing on my screen right here is a Thread CPU stopwatch class that makes it easy to keep track of time, similar to what he did in the book, but this one uses the get current thread CPU time method, which gets time down to the nanoseconds, and it measures only the time being used by your program or your thread, the thread that your program is running in. So that helps eliminate extraneous time where the operating system switches tasks to do other things like updating Windows, and if you're running this in a virtual machine, then some of the CPU time is actually being used by the host Windows operating system and other applications that are running there, and so on and so forth. We don't want to measure that time. We could measure that time and call it noise in our experimental results, but if we can get rid of it, we might as well. So that's the goal of this, and doing it in a class like this, if nothing else, gives you a little bit of experience of writing kind of a useful Java class that we can use in all of our labs going forward. And just makes it a little bit easier to keep track of time. So using this will change the way we write our framework for doing experiments, which I have over here. So let me actually go ahead and make sure I've copied and pasted this into the notes. And I would suggest going ahead and grabbing this out of the OneNote, and let's see, I need to make sure I'm in the right place here. There we go. Let's see. Oh, I don't have a page here for lab number 2. The instructions will be here soon after we do this stream tonight. But under this, I'm going to go ahead and paste this stuff. Let's see. You can't see what I'm doing here, not that you really need to, but just so you see it clearly. So lab 2 instructions will be there shortly. For now, I want you to grab these files. Go ahead and start a new project in IntelliJ, assuming you're doing things in Java. If you're not doing things in Java, you have to adapt these ideas to your own stuff where appropriate, and there's a lot of freedom in terms of how you do that. If you feel confident kind of going your own way as far as choice of language and so forth, then also be confident in your ability to adapt these ideas appropriately, kind of on an as-needed basis. But let's see. So this is thread CPU stopwatch class. So you should grab that, and I'm also going to give you my version of the binary search lab itself that uses that class. So let me come over here, and where's select all? I'm not seeing it. Oh well. There's more than one way to select everything. And let me bring this up and pop that. So you can grab this off of the OneNote, and there we go. And this is my version of binary search performance class. So you can go ahead and start a new project, another version of binary search performance testing. I just want you to do that, get it running. That's actually part of the lab, is copy and paste this stuff and get your own version of this working. So you might as well do that sooner rather than later. And I'm just going to talk a little bit about what's going on here. So let's see, I need to pop back over to here, and all right. So first let's talk about the stopwatch class. So this, if you Google how to measure time in Java, you'll find 2 or 3 different ways to do it. I prefer one that avoids measuring time that's not relevant to what you're trying to test, which is the actual CPU time being used within your program and not jumping around to doing other tasks on the computer. As far as understanding exactly what's going on with this thread_mx bean class type that I'm putting in a variable called magic bean and this management factory and blah, 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 you don't need to know that stuff. Just use this class the way it's written. And for now, I might expand on this, but I don't think we really need anything more than a start method, which will, what it really does is it gets the current timestamp, and then the elapsed time just subtracts that start timestamp from the current timestamp and returns that. So that's just a more straightforward way. It gives us a more straightforward way to keep track of time rather than having to have a start time, end time variable and subtract the difference manually and all that kind of stuff. This just kind of does it for us. And so then we can use it over here in a program that runs our tests. So this is set up to test binary search performance, and I've also broken things out a little bit more to just keep it more organized. So my main program just calls a run full experiment method, and it does this multiple times. So if you haven't picked up on this in the discussion so far, the Java runtime engine will optimize its running of a program while the program is running. So the first few times a method is run, or the first few times through the loop sometimes, may go slower, and by a few we might be talking hundreds or whatever. So for those reasons, you're going to get radically different time results if you run your entire experiment once and then run it again, and maybe even again. I've got it running 3 different times here, going through all the sizes of file that I wanted to test, and Excuse me. And so we'll take a look at what those results look like in a moment. But basically, at least the first one we definitely want to throw away. I went ahead and did it 3 times just to see if there was anything noticeable in terms of the optimizations going from one time to another. And I would definitely recommend that you do that in your own labs going forward. Any experiment you're running, basically do one whole batch of experiments to just throw away, and at least one batch of experiments to throw away, and hope that the Java runtime engine has fully optimized everything at that point, and then you get more relevant tests. Otherwise, you kind of have an apple to oranges test. If on some of it it's partially optimized and on some of it it's fully optimized, you can get you get faster results on larger input sizes and things like that, things that shouldn't normally be happening if everything was running kind of on the same footing. So I definitely recommend doing this. You can even go beyond 2 or 3 times. It just kind of depends, and to a certain extent, just do trial and error on your own system until you feel like you're getting stable results from an experiment. So however much you have to run ahead of time to make things optimized, you just kind of figure that out. As long as it's not taking too long to run. I mean, if it takes 5 minutes to run everything, then letting it run 15 minutes is not that big of a deal. So that's the first thing to note in what I've got going on here. And let me zoom the font in a bit and give us also a larger window to look at here for the moment, so it's easier for you to follow what I'm talking about if you can more easily read what's on the screen here. Okay, so that's all that's happening in the main program right now. You might add some system.out, like I didn't throw this in, but I think I want to. System.out.println running first full experiment ... and we might throw a line like that before each one, and it's just handy to add messages like this as your program is running, so you can kind of keep track of what it is doing and whether it's making progress. So if it's hanging or something, and you'll have some idea how far it's gotten and where it's hanging. And you might decide to stop it if it seems to be taking too long or something. So at any rate, that's the main program. And here is my run full experiment. And what I've done here, another different thing is I'm sending my results to a file, and so you will now have this, isn't it? So particularly those of you that are new or need a deep refresher on Java, can't hurt to have the examples in front of you. This is one way of writing output to a file. I feel like it's one of the more straightforward ways, at least for our purposes, where we don't need anything terribly fancy. So right here is basically opening a file, and it will exit if something goes wrong with trying to open a file to write to. So you can just put that wherever you need, something like this, wherever you need to open a file. I've set the path to the folder where I want the results files up here. And then the file names themselves I am passing as strings into my run full experiment. That way I can have each run of the experiment send its results to a different file. And where I'm putting this, I made a results folder under my home folder. I would suggest doing something similar, but you're of course welcome to organize things however you want to. And then you can see what files are created here. So this is a result file before I did this, and which contained all 3 sets of results, and this is where I've got it broken down into separate results files. I'm going to go ahead, well, no, I think I'm going to keep those around for now, rather than remove them and recreate them. Actually, no, I think I will. Well, actually, no, I'm going to leave these here. So if you're doing this sort of thing, I just want to kind of point out the gotchas and apologies. Some of you, everybody has different levels of programming experience and familiarity and comfort and so forth. So those of you that I'm saying stuff, if you feel like this is obvious, apologies. But I'm trying to bring everybody up to speed on the nuts and bolts that we have to work with, and so that we can focus on the algorithms in our experiments going forward. So, and another thing is many of you probably have not used Linux a lot, so some of this is hopefully new to a number of you. Although if you want to chime in and let me know in the chat here whether this is new, you think this is new and useful versus something you kind of already knew. Ooh, I shouldn't have resized that window. Boy, it really wants to lag on that. So in the terminal here, you can, if you want to create a folder, now you could do that with the file explorer, but I would suggest getting used to doing things with the command line in Linux. So you can make a folder with the make dir command, dir for directory, another word for folder. So make dir results, of course for me it already exists, so it's going to tell me cannot create it because it already exists. And if you want to change what folder your terminal is working in, the cd, change directory command. These are all things you can just Google basic Linux terminal commands and find these things out. It's pretty straightforward. So now we can see that my terminal is actively in my results folder as the working folder. And actually, let me zoom there we go. Make that a little more readable as well when you're trying to watch this in a video. There. So you can see from the command prompt here what folder is the active or current working directory of your terminal. So now if I do a command called ls, which I don't even know what the ls stands for. I always think of it as meaning list or list directory, but I'm not sure if that's anything close to what the ls actually stand for. And we can see the files in there. But more useful for us right now is if we give that ls command the -t and l options. That gives us the long form, and I think I'm going to bump my terminal window up in size here a bit. So this is the long listing, which gives a lot of extra information. Gives us a lot of extra information about each file in our folder. Like the owner, these things off to the side are relevant to permissions on that file. Most important for what we're interested in is the timestamp, and I'll come back to that in a moment. But here we can see that my bin search-exp3.txt was created most recently. The -t option sorts these things in reverse chronological order, so we can see that my third results file is the most recently created, the second one before that, and the first one before that, and the last time I touched this one was a few days ago. All right, so let's come back over to my IntelliJ here and actually go ahead and run this again. I don't think it takes too long to finish, so this should work out pretty well. So now we hit run. It's got to do its rebuild before it runs, and now it's running. And so while it's running, I'm going to talk more about what's going on in my run full experiment. I've done a few things differently than what I had you do before, all of which I think are pretty useful to be aware of. So if we're going to use that stopwatch class, we actually have to create a variable to store a stopwatch object. And I actually have two of them to use in different ways, although depending on which one you use, you don't actually need both of these variables. My trial stopwatch here is not currently being used, but my batch stopwatch variable is being used. So we create the stopwatch so we can use it when we need it later. Then we have the size loop, and the main thing that's different here, and this is pretty important to catch, is that instead of incrementing the size by a constant amount. What we are going to find with most of the algorithms that we test, that what's interesting is the range of performance from very small sizes up to the largest sizes that we can possibly test. And if you do that in small increments, you're going to be running a lot more experiments and generating a lot more data, and your program's going to take a lot longer to run than we really want it to. We actually get more interesting results if we scale up the size to a whole other order of magnitude on kind of each increment of sizes. So what I'm doing here, and this is probably what makes the most sense in most of the things we're going to test, is just start with a minimum input size, and you're going to go up to some maximum size, and we're going to double the size of the input each time. Maybe we'd want to do that and maybe not doubling. Whoops, didn't want to delete all that. Maybe instead of doubling, maybe go up by a factor of 1.5, or maybe go up by a factor of the square root of 2. And I think I would need a math dot in front of that to make that work. See if Java has that. Nope, doesn't have a square root. Doesn't seem to want to recognize square root. Anyway, if we want to throw in a square root of 2, we can look up how to do that. So that would give you more increments rather than just doubling each time. But something along those lines. Have a multiplier. Probably 2 is the largest multiplier you would want, down to maybe something like 1.2 or 1.3, or the square root of 2, or 1.5 might be useful multipliers. But most of the things we want to test, a range of sizes going from very small to very large, and therefore using a multiplier rather than an increment will give us kind of the best range or sequence of input sizes to run our experiments on. So that's an important difference. Let's see. So never hurts to have a few console messages just to show you where you are in the process. So I have a print line to just print out which input size I'm processing at that point. And then we get on to looking at running a batch of trials for a specific input size. So here we have our accumulator variable to represent the total time to run our test function in this batch. So we'll be adding to that or something. We'll see how that works in a moment. Then one thing I'm doing differently here is if you did some experimenting with this, you may have noticed that it can burn a lot of time and you're waiting around for your program to finish if you're creating new input for every test. So sometimes you may want to just create new input, new test input once for each batch, or maybe just maybe you break the batch up into 2 or 3 sub batches and only create new input for those sub batches. That's something to get a feel for, and that we may change that depending on what we're experimenting on. With something like binary search, we can kind of see ahead of time that we don't really need to generate a whole new random list every time we want to test the binary search, because its performance really isn't going to be affected that much by the specific data in our list. With a few oddball exceptions to that. But no kind of real-world test is going to be one of those oddball exceptions, so we're not too worried about it. So here I'm just creating my test list before I run the loop of trials. And then we have some messages. Another thing I'm doing to help get more accurate time measurements is forcing the Java system to do garbage collection at least before I run my batches, because you never know when Java is going to do its garbage collection, which is kind of memory management behind the scenes of your program running, and that can throw off the time. It shouldn't be counted, that the garbage collection time should not be counted in our CPU time of the stopwatch, because it runs in a separate thread, although I haven't verified that yet. But it can still change the state of the CPU and what memory is cached and other issues like that. So we might as well try to force garbage collection to be done outside of our time trials. So that's what this line is doing here. Whether or not that's going to make a huge difference in the data we get, your mileage may vary, but it's worth throwing in there. Okay, so now we're ready to do the real thing, so to speak. So we start our stopwatch. Now this is another difference from what we did before. I'm starting the stopwatch, and I'm going to run the stopwatch for the entire set of trials for this batch, for this input size. So we have our loop that runs all the individual tests of binary search, but I'm having the stopwatch run, I'm starting the stopwatch before that loop, and then I'm going to get the elapsed time after that loop, and that will be our batch elapsed time, the total time to run all the trials. So to get the average time per trial, we have to divide that by that batch elapsed time by the number of trials. Now, why do this? Well, if we're not doing much that's complicated inside this loop other than testing our function, that's not going to throw our time measurement off. Yeah, okay, our for loop, each time we go through this for loop, it's going to do this trial plus plus, it's going to do this comparison to decide whether or not it's going to repeat, and we're generating a new random key to search for each time. All of those are going to take a few nanoseconds at least, and so we're adding, that's being added into the actual time it takes to do the binary search. I'm reasonably confident that the amount of time these take will be relatively small compared to the amount of time this takes, at least when our lists get pretty large. So I'm not too worried about including that time in there. But what I would want to probably avoid is putting garbage collection inside the loop, or putting the generation of the test input. Where is that again? So here's where we create the test list. We do that once per batch of trials. And if I wanted to create a new list for each trial, then I would not want to do this technique of just getting a total time for the entire set of trials, because then I would be including the time to create that list. And actually, the time to create this random list is in the ballpark, if not longer than the amount of time. In fact, it's actually way longer than the amount of time to do binary search. It's probably in the same ballpark as linear search, but for binary search, because it's so blindingly fast, the time it takes to create our list of random data to search is a lot longer than it takes to actually do the search. So we'd be throwing our data way off if we included this in the time. And that's why I took it out and put it before the set of batches. Because A, I know it's not really going to change anything to have a different random list for each test. You might feel like it makes it somewhat more valid if each trial has clean random data. But in this case, it's not really going to change much of anything. So that's what's going on there. Now, there are going to be situations where maybe we do want to make sure we generate clean random data for each trial, in which case you would want to start and stop your stopwatch around every trial. And I've put commented code in here that does that. So if you want to time each trial individually, you would uncomment this line here and this line here, and you would comment out where we start and stop the stopwatch for the entire set of batches. Or you would, you could do both. You could measure it both ways, but then you'd be including the time to start and stop the stopwatch in your trials, and that actually might add a little bit more significant amount of time. So again, this is something to kind of be a judgment call depending on what we're testing. And how long it takes to run the test. So once it gets the average time per trial batch, then it prints that data to a file, and again using this results writer up here that is created way up here. So up here is where we open our output files, our output file for the results, and ultimately we create this results writer object. And if you want to see what data type that is called a print writer. So these are defined in the Java libraries. We have to have this file writer object from which we then get a print writer object. And so we create that file writer with a new file writer, and then we create the results writer or the print writer, store it in this variable. And so now when we actually want to print our results, we use that and we can print. And I prefer to format my results, so I'm using a printf. I'd forgotten that Java actually has a printf that is similar, not absolutely identical to the C programming printf, but in most respects it'll work the same way. For the simple stuff, it should work about the same as what you're used to. So formatting it just makes the data easier to read when I go to actually look at it. So just a quick review on that. Printf, you give it a format string. You have format codes that start with %, and then D if you want integers, F if you want floating point numbers, and you could put a number in between the % and the letter to just give it basically a column width. And if you have decimal number or fractional numbers, floating point numbers, you can have a number and then a point and how many digits after the decimal point you want to see in those numbers. And that takes care of the format. And then you close the format string. You do need a /n in there so that your format string so that it prints to the next line each time. And but after your format string, then you list your variables that will substitute in there. And I also add this .flush method from the results writer. That forces this stuff to go out to the file immediately. Otherwise, it may buffer it for several lines. And if you're trying to watch your file grow while your program is running, you may not be seeing output that's waiting in the buffer. So if you use this flush, that forces the output out of the buffer so you can see it in your file immediately. And we'll see that in action in a moment. Okay, so if we come over here, since this has been running, let me bring up my terminal. And if I do the ls-tl in my folder here again, we see that once again it has recreated my 3 files. This ls-tl, if you're running multiple repetitions of your experiment and the results are going to different files, this is how you can make sure that it has actually completed and that your files are up to date in the right order. If you saw, say example, your number 3 file is lower in the list here than your number 1 and 2 file, then that means it hasn't finished writing that file. And maybe your program crashed, who knows, or maybe your program's still running. But don't let yourself get thrown off by overwriting only some of your data and looking at old data on some of these files. And again, I know that's probably obvious for some of you, but it's the kind of gotcha that I just want to help make sure everybody avoids. And if I say it up front, and hopefully I'm not saying it too fast and you're following what I'm saying, that is one thing I'll say. If you're out there listening live and it seems like I'm just rattling stuff off too fast or something, go ahead and ping the chat and say something that you're not catching it or whatever. So at any rate, let's go ahead and actually look at what's in these files. You can use, if you just want to list what's in a text file, in Linux there is the cat command, which, believe it or not, that's short for concatenate. And what does concatenating have to do with listing files? Well, it's actually a way of, when this command was originally written, it was kind of a way to concatenate multiple text files together, one after the other. So you can actually do multiple files after this, but often you just use it to list what's in a single text file. So if I want to see, say, what's in my exp1 file, my first experiment, we can see the data for that. We can see the time values. We can see the input sizes. Notice that I have put a hashtag and then a hash symbol and then column names. And that gets at how we're going to use this file in just a moment to make plots. Now, that's the other thing I wanted to make sure I showed you before I asked you to do another lab. That's why, again, part of the reason that I put off posting lab instructions is to talk about a way to do the plotting. Now, you could all probably come up with your own way to do plotting, but I think I'm going to show you GNU plot, which I think is one of the easiest, more straightforward ways to do plots. Even if you're using a different language or whatever, as long as you can get your data into a nice text file like this in columns, GNU plot, I think, is one of the better ways to get plots. So let's go ahead and what was I going to say? Oh, and the thing about GNU plot is when you generate text files of data, the hash symbol indicates a comment line, and so when you use a file as data for GNU plot, that means it will ignore that line. So it's an easy way to get column names into your file, but not have it affect the data or the plotting. So, so that's my first file. If I want to look at the second file, I can again use my cat file, xb2.txt here. And there we go. And notice the difference here. And this again comes around to Java and its optimization. So we can clearly see that the first few times we did our tests, especially, we're getting quite different results. 1300 nanoseconds versus 150 nanoseconds. 270 versus 112. There's still something going on in terms of optimization. I think it's optimization of the loop, not the method, where the shorter list, the list of one element, searching a list of one element, still is taking longer than searching a list of two elements. But then at that point, at least it seems to have been optimized, and our results look pretty good. There's still some stuff that goes on, apparently, that gives us a little bit weirdness. For instance, at about 262,000 items in our list, it took 1,300 nanoseconds, and then it only took 1,000 for a list twice as long, and it still took less time for a list 4 times as long. What's going on there? Difficult to say. I have some ideas about why sometimes it ends up taking longer, but I can't be absolutely certain. But it is something to be aware of. This is going to make our data look a little bit wrong in terms of what we expect theoretically. Certainly when it comes to searching, we expect it to take a lot less time. Or I should say we expect it to take more time, at least a little bit more time, for longer sizes of lists. And doubling the size of the list should definitely make a notable increase in the amount of time it takes. But we do see that it does tend to grow. It's not quite as smooth as we would like, but we do see a general trend going up. But even here we see that the this one even is taking longer than a file 4 times as long again. And there we're getting up to, I think that's 500 million. Yeah, about 500 million items in that one. So, but that's our second test. Let's see if the third test looks any better. So here's the third test, and whether it's something Java did behind the scenes to optimize or something else going on, this one looks a little cleaner, although we still have, well, no, it's just doesn't jump out to the eye. So there's one that is taking a lot longer than a couple of the smaller files that come, or a couple of the larger files that come after it. Here, at least, our longest file is taking the longest amount of time. Or I should say not our longest file, but our largest amount of input is taking the largest amount of time. So that's not too bad. One way you can clean this up a little bit more is by running a larger number of trials. Now this took a few minutes total to run, so to a certain extent you have to make a judgment call about how long you want to wait. And so as you're doing labs going forward, one of the things you're going to want to do is look at your maximum input size and so forth. Where is... What am I doing? Oh, I'm looking at the... Oh, I have another project open. I'm looking at the wrong one. Let me bring the one we've been looking at up. So scroll back up. Okay. So here I'm choosing to do 100 trials. They go by fast enough that don't have to wait around too long for that. I'm taking my max input size up to 2 to the power of 29, which, if you remember, 2 to the 30th is around a billion. It's starting to get like maybe 1.2, 1.3 billion, I think. But 2 to the 29th, half a billion. That's about as big as I can get with the amount of memory I have. I think if I go 1, I might be able to go to 2 to the 30th there and have it not run into a heap space issue. Again, just to reiterate, if you haven't caught it before, do try to give your virtual machine, if you're using a virtual machine, as much memory as possible. You do that in the machine settings, system, and you have base memory that you can set here. So right now, I've given my virtual machine 12 gigabytes. My desktop has 32, so I could actually probably bump this up higher. A lot of you probably only have 8 or 16, I would guess, are the most likely amounts of memory that you have on your laptop or desktop that you're doing this class on. So you're not going to want to give your virtual machine all the memory that your host machine has, but a good fraction of it is probably okay as long as you're only doing work on the virtual machine. Now notice that right now this is grayed out. I can't change this right now because my virtual machine is running. So you would need to actually shut down your virtual machine. You can't just do a save state like I can do here. I can save machine state, but you still can't change settings like how much memory it has when the machine is paused in stasis, so to speak. You need it to be properly shut down, and in that case, you want to shut it down cleanly with the shutdown option here. Then you can go into the machine settings and bump up the memory. The other thing you need to do to use more memory is come into your edit configuration. So that's the run menu in IntelliJ and edit configurations. And you want to set these options here. This is one I'm experimenting with. I'm not sure if this is one that's going to make a huge difference. But these two options here determine the amount of heap space. The -XMX option is the more important one, but I would just say put both the XMX and the XMS in and make those as large as you can. You can use G for gigabytes or M for megabytes and just put whatever number is appropriate here. I'm actually telling it that it's allowed to use more than is really available there. I hadn't noticed that I left that at 16. Since my virtual machine only has 12, it doesn't do me much good to make that higher than the virtual machine, so I'm going to change those to 12 now. Probably wasn't hurting anything, but it wasn't going to be able to get that high anyway. It wasn't going to be able to use that much memory anyway. In fact, even getting to 12 is pushing it, even if I set these to 12. So if you want to get a sense of how much memory is needed, again, we're building these lists of longs, right? So let's come down here. Long test list, create sorted integer list. If we go down and look at the method that actually does that, this is what I came up with, and it's more or less what I suggested in the instructions for Lab 1. So we're creating an array of size long, but you need to know how many bytes is a long. So in Java, a long integer is 8 bytes, 64 bits. So if we're doing 500 million 8-byte integers, that should be only about 4 gigabytes. But I think, I don't know, if I trying to remember when I tried to go up to 1 billion, that would need a little over 8 gigabytes, which should still fit in the heap space I have allocated, but I think when I tried that, it still ran out. And that's because your available memory becomes fragmented. It has to be able to get an entire contiguous chunk of memory of the size that you're asking for. And if it can't do that, it's going to give you that out-of-memory error or heap space error and fail. So up to about 500 million is as large of a list. You're probably not going to be able to get quite that high, but that's all right. Just do your best with the system you have to test the largest inputs you can. And another thing is, with binary search, this is probably the last algorithm we're going to test that runs so fast, even on very large lists. So once we start looking at sorts and other algorithms, those algorithms are going to take substantially longer on long lists. So then we're going to be constrained by how long do you want to wait around for your experiment to finish, rather than how much memory does your computer have. So there we may not be even hitting, we're much less likely to hit memory limits. So that's another thing to keep in mind in future labs when you're doing these experiments. So just once again, that's in Run menu, Edit Configuration. You want this XMX and XMS, and you set the heap size in both of those. Just leave them the same. I'll go ahead and mention this -X comp option that I also put in here. I put that in there to see if I could get it to force it to compile and fully optimize. It's clearly, if you just look at my results, clearly it's not starting off fully optimized, so that didn't work. This might give you somewhat better results. It just forces it to compile everything up front, but then again, maybe it won't make a whole lot of difference. But that's something you might experiment with, but it's certainly not hurting anything as far as I can see. I haven't really been able to confirm whether I'm getting much benefit out of that. Okay, so yeah. Where were we in here? So let's see, I've gone through our trial loop. So your trial loop, again, that's just counting however many trials you want to do. So that's the other thing you can do to hopefully get better results, is do more trials. Right now I'm doing 100, so an average out of 100 should give us a pretty stable result. So the fact that we're doing an average of 100 and getting results that are not as consistent as we would like to see. Again, if we come look at our data, larger list, taking more than twice as much time to search for some reason. Why would that be happening? It's one thing that you could suspect there is that maybe somehow my random list that I generated isn't as random as I think it is. So, or maybe it does matter. Where is it? So here where we're generating one test list for the entire batch, maybe there's something about that test list that it's generating sometimes that makes all of the searches cut short. That would be rather strange based on how I make it. It's basically a succession of numbers that increment from 0 to 10 from the previous number. There's not much of any way that most of these searches, when we're searching then for a random number in that range, there's not much of a way for most of those searches not to take the full number of steps of looking at the middle, jumping up or down, looking at the middle of that half, the middle of that half, and so forth. Zeroing in is normally going to take the full log 2 of n steps for the vast majority of these trials. So it's not very likely, unless I've done something boneheaded and haven't noticed it yet, it's not very likely that the test list I'm creating here is the cause of these strange results. It's more likely some underlying optimization either in the hardware or in the software. It might be something about the Java virtual machine where at some point it's doing something optimal and then it's not doing something optimal. Or it might be, and this might represent, like I said, I don't think we should be getting garbage collection added into our times. This might be caused by garbage collection and the amount of time it's spending doing garbage collection. But it also might have something to do with the CPU cache and memory, that in certain situations it's getting the memory cached and then sometimes it's not. And it has to recache memory. And we might be seeing some jolts resulting from something like that. It's maybe not too worthwhile to speculate on. But we can bump up the number of trials per batch to see if that smooths out these kinds of things, because odds are it's one trial in particular, or one or two trials in particular, and my virtual machine's lagging again. There we go. One or two trials in particular that are going exceedingly long and throwing these averages off, rather than all of them going wrong. And so we might do a larger number of trials so that this kind of thing gets wears out, gets kind of rubbed out in the averaging. So let's go back over to IntelliJ, and we can bump up the number of trials. I think earlier I did 1,000. I'm not sure how long this is going to take. I don't think it's going to take too awfully long, even at 1,000. We can kind of monitor the progress down here after it finishes building. So there we go. And starting the first experiment. So the first few, even though it's doing 1,000 trials each, not taking too long. We're up to several million per list. Now we're starting to see a notable slowdown. See what we're at here. Let's see, we're already at 134 million. It's going to go up to the 260 and then the 500 something, and that should be it for the first experiment. So it looks like it's taken less than a minute per experiment still. So we could still bump up the number of trials. We might, instead of multiplying size by 2, we might get more data by making our multiplier, instead of a multiplier of 2, maybe use 1.5 or 1.4 or something like that. All of which would be fine. Let's see. So, and again, I do recommend that when you're doing this stuff on your own, add these kinds of printout messages just so you can see what progress your program is making. So you're not sitting there staring at a flashing cursor and not sure if your program is making progress and so forth. Because you are gonna find that you have to run it over and over and over again while you're debugging and testing, and then kind of figuring out, well, how high can you go in terms of input size and things like that. So those are all things to consider. So I think I'm still in the first full experiment, and this last one is taking a while. Okay, so that's the first full experiment. We can go to our terminal now and see what's going on. I'm going to do an ls-tl, and now you can see, okay, my experiment number 3, that's old data. My experiment number 1 has finished again, and the experiment number 2 file is at least partly written at this point. And we can do it again and see where we're at. Okay, it's still somewhere in the middle of experiment number 2. So we can see what's in our experiment number 1 file. And just as this is a quick tip on using Linux. So you'll notice that I'm starting to type and suddenly it'll jump. if you type the first few letters for most of these commands, if you type the first few letters of a file and then press tab, it auto-completes for you. And then, but it only auto-completes up to what's in common with with multiple files. So there it stopped at exp because there's 3 files that start with those letters. So then I add the 2 and hit tab again, and it finishes out for me. Just a tip that can save you a lot of typing so you can enter these commands faster. All right, so here's our, actually I wanted to look at 1 because, so we can see that it's still not quite finished with experiment number 2 because it hasn't done the 500,000 size file, or the 500 million. So I actually wanted to look at experiment 1 first because that one was complete. There we go. And again, I'm throwing away the data from the first because that's usually not optimized. Although, interestingly, we didn't get the really long time on the first trial this time. And that might be because we're doing 1,000 trials and averaging out. So most of the optimization might be happening now just on running it on input size 1. But we do see that there's still some weird stuff happening. Like this one took incredibly long compared to several much larger input sizes. So something strange happening there. But we can see generally it looks like we're getting pretty good data, not always consistently increasing. So again, there's some optimization quirks or something going on where we're measuring time that we didn't want to measure. Or it's garbage collection or something going on behind the scenes. But not too bad. So let's go ahead and probably experiment number 2 is finished. And, well, we do see that there is still some optimization that went on. So here the times were in the 200s. But down here we see with the second experiment, they're closer to 100 all the way up to input size of 64. Now keep in mind here on these really small files with binary search, again, what does binary search do? It makes a comparison and then jumps to another index. Makes a comparison, jumps to another index. Each of those steps takes a few nanoseconds, right? So just the amount of time to assign things to a variable or to call a function, all of those kinds of things take a few nanoseconds. So what we're really seeing here, since with all of these being almost the same time, right up until there actually, what we're seeing is that the overhead of calling our functions or doing our loop, that's what we're measuring here on these really small files. So this data is almost throwaway data because it's just our function itself is going so fast that all the other stuff that we're measuring in that time is outweighing the amount of time it's taking to do the search. So in a sense, you could probably look at probably from here forward, or maybe we'd even want to go from maybe here forward. We might want to subtract about 100 nanoseconds off of all these times, and that might actually be a somewhat more accurate measure of the actual search time in our search function. Because most of this that we're seeing here, these 100 nanosecond times, that's probably overhead. Again, if we go back to our code, we're measuring the amount of time it takes to do this trial to increment that variable, to do this comparison, to generate this random number as the number that we're going to search for. We're measuring the, there's included in the time to run this binary search function. If we come down here, here's the binary search function. Well, there's a certain amount of time it takes to call the function, to do this initial stuff before we kind of even get into the loop. It's this loop that's going to take the log2 number of steps bouncing around in the list to zero in on the number that we're searching for, on the key that we're searching for. But there's always, a certain amount of time to do this stuff, a certain amount of time just to jump into the function and pass the parameters. All of that takes a little bit of time, and that's what we're seeing here. when we're measuring these really, really fast ones, most of that is that overhead of calling the function. It's not really the log2 of n part of the process that we're measuring there. Somewhere in here, once we start to see results sort of consistently increase, although not as consistently as we would like to see theoretically, we're seeing reasonably consistent results here now. Yeah, that one still looks bad, but not too bad overall. Somewhere around list sizes of 32,000, 65,000 is where we really are starting to, now we're really starting to see the impact of the efficiency of our algorithm versus the overhead. Let's go ahead. I think by now our experiment number 3 has probably finished. Let's do an ls-tl here. And yep, we can see that, well, at least it's the most recently touched file. Let's see if it's finished. So let's run our cat command. And there we go. So we're getting data. That's looking very similar to the experiment number 2. So probably most of the optimization has cleared things out. Has cleared out. We are still seeing occasional times when we get these weird jumps, whether that's because that happens to be where some garbage collection kicked in, or who knows what. Something happened at that point. It'd be interesting to see if that's consistent from experiment to experiment. So that's on the that's the first time we get to roughly 1 million. And let's see what happened at 1 million up here. Nope, that's not jumped up. In fact, we don't get jumped up until we get to around 60 million. It looks like there we have one that pops out that looks kind of wrong. In here, everything looks pretty reasonable. These two are, well, this one went, these two are a little bit faster than one that's a quarter that size. So this one is a little high, but not hugely out of line. This is the only data point we have out of line in our experiment number 3. And so that's even with trying to do averaging over 1,000 trials. So that's just so the main thing I want you to see here is see it in my results, that this is kind of what we're going to get. Now, I've previously taught this class and used C and C++. You get somewhat more consistent results, because with there, you're just compiling to native machine code, and you don't have any runtime optimizations going on. You don't have background garbage collection going on and things like that. And that's most likely where we're kind of seeing these things, seeing these numbers that just don't look right, where we have one clearly taking a lot longer than it should, and so forth. But this isn't too bad, and it's kind of just what we have to live with, I think. And again, when we run algorithms that are not so fast, so that on an input of the size of 100,000 or something, an algorithm that takes 4 seconds instead of let's see, this is 1,000 nanoseconds, so that's still 1/1,000,000th of a second to do the binary search on a list of 1 million. Okay, so searching a list of 1 million things is taking basically 1/1,000,000th of a second here. So that it's going so fast that basically noise, some kinds of noise, are impacting our results here that may not hurt us quite so much when we're running tests on algorithms, say bubble sort, merge sort, and so forth. Those are going to take a lot longer once we get to much larger files, and hopefully that will reduce the impact of noise, so to speak, on our results. But at any rate, this is our data. So let's see, is there anything else I want to say about how I've implemented this? Yeah, so forcing the garbage collection might at times just make your whole experiment take longer. So again, whether you want to try to do this force garbage collection, you can comment that out, see if that makes much of a difference in terms of your results, how long things take, and so forth. Whether your results come out more consistent or less consistent. And you might also try, if you're measuring the time of every individual trial instead of the whole batch of trials, you might try forcing garbage collection before each trial. I do think that's going to end up, because garbage collection tends to take a while, so doing that before every individual trial might make the whole process take a whole heck of a lot longer. So your mileage may vary there, but it's something to think about. And again, if we're in a situation where we want to generate an entire new list of input for each trial, then you will want to measure the time of each time individually and accumulate the total. So here I'm doing batch elapsed time equals itself plus the stopwatch elapsed time for the trial. That's what's in this comment here. So if we uncommented this and this, we would want to comment that and that. And if you did that, then you could get away with maybe doing garbage collection before each trial. That way it's highly unlikely to then do garbage collection during the trial. That sort of thing. And that might improve our results somewhat, but it makes your whole experiment take longer to run if it's doing all that extra garbage collecting. So those are just some things to consider when you're playing around with this and trying to get good results and make your results look as good as possible. What else do I want to say about this? Yeah. So hopefully between having me talk through it and having the code yourself to play with, this gives you a better idea. This will give you a pretty solid idea of what to do going forward. I did want to show you like the idea of measuring time for the entire batch. One of the other reasons I did that is because, especially for really fast processes, just doing the start and elapsed time methods takes some time. And you would end up adding some of that time into your time measurements. So the actual, trial stopwatch elapsed time, and actually just doing this addition, this assignment, and this addition, and running our trial stopwatch start. Some of the time to do that ends up being added into our time measurement for each trial. That can throw the measurements off a little bit. And as I was playing around with it back and forth, I found, at least for this binary search where it runs very fast, measuring the time for the entire batch seemed to give me cleaner results. Again, your mileage may vary depending on what experiment we're doing at the time. So that's just something you make a trade. You might try it both ways and see what your results look like. Let's see, some other things I want to mention. Yeah, so when you're developing this, when you're developing your labs, you can probably almost copy and paste this and then just start editing. But one of the things you're going to want to do, particularly when you're debugging, you are definitely going to want to do a smaller number of trials, maybe even only one trial per batch initially, just so that your tests, your debugging tests, go a lot faster. You're also maybe going to want to come in and make your maximum file size or maximum input size a lot smaller. So maybe you only go up to 2 to the 10th or even 2 to the 20th, as we saw. A list of 1 million didn't take that long. And all you need to do there is, if you find when you're testing it and trying to debug things, if it's taking too long to wait around to see what happens, just bump your maximum input size down until it's not taking too long. If it's taking too long when your maximum input size is really small, then you maybe have a infinite loop or something that you need to fix. But that's definitely something you can save yourself some headaches with. So consider bumping your max input size, consider bumping your number of trials down, trials per batch down. And then the other thing is, and you may not want to do multiple experiments. Maybe you want to, you would maybe want to comment out your extra experimental runs when you're debugging. So all things that you may want to keep in mind when you're doing this on labs going forward. Okay, so anything else I wanted to say here? Let's see. I've been talking a lot. This hasn't been a very interactive stream tonight. Just to check who's out there. Do I have a live audience at all right now? Chime in and just say something, just so I know I'm not alone. And let's see. And do you have any questions about what I've said so far, or is it all pretty straightforward? And I'm gonna go grab another soda. Is anybody actually doing this along with me? Or are you waiting to go do it to do it later? I might be rattling off stuff too fast for you to just keep up and do it right along with me. But maybe not. I don't know. Okay, well, that's the benefit of having the video archive, that you can go back and skip over the boring parts and get to the important parts and pause and whatever you need to do. So at any rate, let's see. What else do I want to say tonight? I think I'm going to keep tonight's stream focused on what you need to do for the lab, and then I'm going to go finish writing the formal lab instructions so that you can actually get started. Definitely, you can start by, you can start working on a merge sort function anytime you want to, if you haven't already, in Java or your preferred language. But the other thing I want to talk about tonight is plotting. Just curious, those of you who are here with me live, or even if you watch this in recording and you want to say something in the general chat about how you may or may not be inclined to plot data. How many of you have a method of plotting data that you're already comfortable with? Like maybe you would just, maybe if I didn't suggest anything or expect anything, you would use, maybe you might just use an Excel spreadsheet and plot data that way. I highly recommend not doing that. I find that Excel very awkward as far as getting nice plots, particularly from a scientific perspective. I guess from a business perspective, maybe the plots look fine, but you just don't have very easy way to control what the plots look like and so forth. But I'm just curious. PyGal. Yeah, I'm not familiar with PyGal. LaTeX is probably a good one. I'm going to show you all GNU plot. Unless your preference is strong, you might want to try playing around with this. It's pretty easy. So GNU plot, I've set my program up so that it prints the data out in exactly the format I need to use in GNU plot, which just straight up text, columns of numbers. Again, I think I mentioned earlier that you can use the hash symbol for comments in your GNU plot data files. So it makes it a pretty easy way to create data files. And then to run GNU plot, well, you actually will need to download the package. So you can do a sudo apt get install GNU plot. I've already done this, so it won't actually install anything. It'll tell me it's already there or it's up to date. So in my case, it's telling me GNU plot is already the newest version because I already have it on here. But if you run this command on your Linux system, then you'll be able to run GNU plot. That's basically all there is to it. There's an alternative way you might prefer in the administration tools here, software manager. I think this is how I showed you. Actually, I think this is how I downloaded GNU plot more recently. And you can get GNU plot this way. I don't know that it makes much difference which version of GNU plot you grab here. I just grab the base one. I might experiment with the X package one just to see if there's any differences to make it a little bit nicer to use or something, but you can get it this way as well. That's the software manager within the administration tools on Linux. So two ways to do it. Get that. But once you have it, all you need to do to use it is you type GNU plot on your command line here, and it's all GNU plot itself is a command line interface. You can write scripts for it, which we'll get into later. For now, just command straight in here is fine. So within GNU plot, if you want to plot data that's in a file and it's nicely, and if it's in the simplest format, about the simplest format is you have a column of values for your x-axis and a column of values for your y-axis, and you don't have anything weird going on like missing data values or anything like that, and you don't want to have things like error bars and yada yada yada. This is the most straightforward kind of plot we can do in GNU plot. Later we'll look at like maybe you have multiple columns of data because you want to compare two different things or something like that. But for now, this is fine. So let's go ahead and plot our data. So to do that, the simplest plot command is just plot, and then you give it the file name, and it'll just pick out automatically. If you don't tell it to do something different, it will just pick out the first column as X and the second column as Y. And so here, and actually GNU plot is smart enough to do the file completion with the tab, so you can even just type just a few letters, hit tab, and have it complete your file name for you. And just put the file name in quotes, single quotes. Off the top of my head, it might accept double quotes as well. It probably accepts both, but I'm using single quotes here. And that's the simplest plot command. Now this won't look as nice as we might want it to. So let's take a look at what we've got here. Let me magnify this a bit. And notice that almost all of our data is squashed down here almost at 0 on the x-axis. That's a consequence of what we're choosing for our input sizes, which is our x-axis. So these are our input sizes. And so 1, 2, 4, 8, blah, da, 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 da. Because we're doubling every time, our input size is increasing exponentially. So these sizes of, 100 million, 250 million, 500 million, that ballpark, that just makes most of these look microscopic by comparison. So when we look at our plot, we see most of our data points are squashed down here on the x-axis. So this is, and again with our kind of weird data, with this data point being, actually these two both taking longer than our largest file size, which again is a little odd, but again we just kind of have to put up with that kind of noise in our data, it looks like. Let's see. This plot is not really showing us what we'd like to see, because a lot of the information is so squashed down here on the x-axis near 0 that we can't really see what's going on with that data. So if we're going to have our input sizes increase exponentially on our x-axis, we may want to do a logarithmic plot, at least on the x-axis. So the way we can do that is, before you do the plot command, you can do, let me double check the syntax. Yeah. You can do set log scale, and then what axis you want to have a logarithmic scale on. So in our case, let's try just the x-axis. So you can say set log scale x, and that command will make our x-axis logarithmic. And so now if we do our plot command again, now we see our data looks like it makes a bit more sense, right? We can see that it's pretty flat here in the vertical now for all of our smallest file sizes, from 1 up to file sizes of around 10,000. We're not really seeing any trend of increasing, maybe ever so slightly, but it's hard to see. But we are definitely seeing a increasing trend after file sizes of about 10,000. And that's actually what we really care about. What happens on the smallest input sizes is not terribly interesting, because it's when you have large input sizes that you're typically going to be worried that your algorithm's going to take a long time. So small input sizes, you're seeing just little bits of overhead and so forth. It's not really relevant to the efficiency of your algorithm. Whether you're doing, like things in merge sort, are you doing a bubble sort or a merge sort? Small file sizes, you probably don't care that much whether you do a bubble sort or a merge sort. But later on, if you're looking at large file sizes, well, bubble sort, that's going to take time proportional to the square of the size of your input. So that's going to curve upward and get to very long times, sorting times, as your file size grows. Merge sort is not going to grow, the amount of time is not going to grow nearly as drastically. But it's all in the larger file sizes that we really care about that growth, because that's where you're talking about minutes or hours or days or months or years of runtime, rather than fractions of a second of runtime. But we still might get a better looking plot if we make both axes logarithmic. So you can go back here, and instead of set log scale on the x, let's set log scale on the x and the y axis. And then we can plot bin search that file again and see what we get there. Now we can see much more of a trend. We can see that with the very small file sizes, we're seeing you can see a slight trend there. There does seem to be right around 10,000, right around a list of 10,000. There does seem to be a break where the trend changes quite a bit. I have my theories about why that happens, and I suspect it may have something to do with page caching. So depending on your knowledge of CPU hardware, most of you are at least aware that CPUs and computers have a spec which is their cache, and it'll be however many megabytes or gigabytes or whatever. I think gigabyte caches are still pretty uncommon, but hundreds of megabytes or 64 megabytes or whatever cache in the CPU. It's basically, the cache is a small memory, small but very temporary memory, and so it takes chunks of the main memory, brings those into the cache, and if something is if it's trying to access data in memory that's in the cache, it can do that much more quickly than it can access that data from main memory. And so there's that underlying optimization that the CPU is trying to do. It's always trying to cache those pieces of memory that it needs to access more often than other pieces. So there may be something going on where when our list of numbers is large enough, so at 10,000, you're talking about 8 bytes per number, so you're talking about something around 100 kilobytes of data when our list gets up to be about 10,000 long. So maybe, below this, maybe all of that can be kind of simultaneously pulled into the, and this is big emphasis on maybe. I'm just speculating here, but it's worth the kind of thing to think about that might be going on. Maybe our CPU is able to pull the entire list into the cache and run a lot faster. Now it is still going to take a bit longer on larger input sizes, so we can see a very slight increasing trend here. But still, that trend is quite different. We see a break in the trend, and then we see a different trend at larger than about a list size of 10,000. And that may well have something to do with how much, whether it can pull the entire list into the CPU cache or not. That's one possible reason we might be seeing this different trend. We're more interested in the trend here, which is more or less what we would expect. We would expect it to be, this looks kind of like a straight line, right? So we expect kind of each, as the log of the size of the input increases, we expect a result that's proportional to the log, and that seems to be roughly what we're getting here. So when you go to plot your data, you need to think about, do I want to use a standard plot, a semi-log plot where only the x-axis is logarithmic, or do I want to use a double log plot, a log-log plot, where both axes are logarithmic? And depending on what your data looks like, it's easier to see what's going on in your data depending on those choice of axes. Most of the things we do, you'll probably want to have your x-axis on a log scale, and you may or may not want your y-axis on a log scale. So that's how to plot your data. Let me show you a couple other things here before we wrap it up. Let's see. So there we are only seeing individual data points. So you can add some options to the plot command. In particular, you may want to throw a line in there. It just kind of makes, I believe lines points is the option. Yeah. So you say with lines points like that in your plot command, and then your plot now connects all the points with lines. And I think that makes it a bit more readable, or a bit more viewable. So go ahead and do that. So for your lab number 2, this is about as sophisticated of plotting as I'll ask you to do. I just wanted to get you comfortable with GNU plot if that's what you go with. If you have something else that you prefer, that's fine. But you might want to play around with GNU plot, just something new, learn a new tool. It's pretty handy. You can easily Google for tutorials on GNU plot if you want to get a little bit more fancy with your plots. But I'll probably be giving you more tips next week on things you can do with GNU plot. But this is about as much as I'm going to expect for lab number 2. You might want to Google how do you label the axes or put a legend in or something if you want to make it look really nice. But this is the main thing I would want you to get. So you'd get just get a screenshot where you show you're plotting your data, and you do want to label your screenshots somehow. But you can just you take your screenshot, put that in a Word document or something, and then you could just give a caption explaining what the chart is actually showing, which will be fine. So that's GNU plot. That is hopefully gives you a good rundown on the kind of thing I'm going to expect you to do on your labs. I think this experimental framework, at least in a Java environment, I think is going to work pretty well for us. I'm a little bit disappointed in the inconsistency of results, but I think staying consistent with the language the textbook uses is probably a good idea. Oh, that reminds me of one last thing to talk about. So in the textbook, well, one of the things he does is he does have this. He has his own stopwatch function. Where is it? Yeah, or his own stopwatch class, and I'd say don't use his, because this function that he uses, first of all, it doesn't go to nanoseconds. It only goes to milliseconds. Although measuring to nanoseconds, we probably aren't going to get very good results down to the nanoscale anyway. But the other thing, this is measuring wall time, or wall clock time, the actual, just the passage of time. So if your host computer or your virtual machine is busy switching to other tasks while it's running your program, which it inevitably will be, you're including that time in these measurements. So don't use his stopwatch class here. And he does have some, and if you've read through all of this, he refers you to the website that goes with the textbook. You can download that stuff, and if you want to use that stuff, that's fine. Like, I think up here in section 1, where is it? He sets that he's provides this thing called standard draw. Where is it? You know what? There's a search function that would make life easier. Trying to get where he has the example. So he has this thing called standard draw, which you can use to plot points and lines and so forth, and use that. That would be an alternative way to plot your data. I'm definitely not going to require that on this lab. This is something I might have us use later on. But if you want to experiment with it, it could be fun. It could also, you can use it not just to plot your data, you could use it to visualize sorting. So as you can see here, he's showing different ways of visualizing sorting, so you can actually, the data that you're sorting as the height of the lines, and you can see them moving around as it sorts. And if you Google, you can find animations on YouTube that will look very similar to the kinds of things that are going on here. But we're more interested in the performance, not in the how to visualize the sorting going on. And there's a lot of algorithms that it's just going to be too much extra work to do the visualizations anyway. So I'm not positive that there's a great deal of value in messing around the standard draw, but it might be fun. So if you want to use that, and if you want to use that to generate your data plots, you're absolutely welcome to. And if you're trying it out and trying to figure something out, just chime in to the Discord, and I'll see if I can help you out getting that set up. I've done a little bit of playing around with it, got some of it working, but not all of it. And so, like I say, I can probably help you get it working if you run into trouble. I don't think there's not a whole lot going on that's too difficult to mess with. But I just wanted to call your attention to that. If you haven't done this reading and you haven't looked at these sections yet, he's going to phrase, the exercises in the book. I'll probably have you do some exercises out of the book. So far, it's all been stuff that I've developed as far as what I'm asking you to do, but it's similar to things he's going to ask you to do in the book. He's going to frame things in terms of these libraries. So if you want to mess around with them for now, that's fine, or you can just focus on the lab instructions as I present them. So basically for this lab, what I'm going to ask you to do is do what we just did in this video, just basically copy and paste my classes, get them running, maybe do a little bit of experimenting with different, because depending on your system, you may not want to make your maximum input size as big as mine. So you're going to want to do some experimenting to see how many trials you can do, how fast, and how big of an input size you can get to work without either waiting too long or having it run out of memory. So you're going to do that. Then you're going to do a new project, and instead of testing binary search, you're going to do merge sort. And when you do merge sort, you're probably not going to get anywhere near half a billion lists of half a billion. And you're probably not going to do huge numbers of trials, especially for the larger file sizes. Let's see. And then the third thing we'll do is probably, this is something out of the book, it's not one of the exercises from the book, but he does this three-sum here, this three-sum problem. It's pretty straightforward, so you're going to want to read, so I'll direct you to read this section if you haven't already to know what that's about. And I'm going to want you to just run experiments and generate data on this as well. So not a whole lot of original coding. You've got the merge sort, you've got pseudocode from me on that. It's also something you can Google and find any number of examples on merge sort. I'm not asking you to invent your own merge sort code. You may, if you look up examples, you may have to do a little bit of adapting to get it working within the context of your larger experiment. But it shouldn't be too bad. So those are the things I'm going to want you to do, is what we just did, then do basically the same thing, but test merge sort instead of testing binary search. And then once more, we're going to do tests on this three-sum algorithm and get performance tests on that and get the results and plot the results. So it's basically going through the motions of doing some of these experiments, getting results, plotting the results in whatever method of plotting you find most copacetic. Whether you want to use the GNU plot, as I showed, which I recommend. If you don't already have a strong preference, definitely use GNU plot. If you have another preference, that's fine, but I would suggest trying GNU plot just as something new. So let's see. Looks like I've got the runtime under 2 hours tonight. I think rather than diving into anything else, I think I'm going to leave it at getting you as prepped as I can, I hope, to do the lab that I'm going to ask you to do. And so I'm going to go here and finish writing up my formal instructions, so you should see those in a matter of minutes, half an hour at most. You can certainly get started on a merge sort function. You can just kind of mess with that in and of itself before you've seen the instructions, and then the instructions will just be there to clarify formally exactly, so you have a better, clearer idea of exactly what I expect. But getting started to do the merge sort, or maybe do this three-sum and start playing around with that, are things that you can already do. So yeah, so any questions before we close out the stream? And if you don't have any questions, just say good night or something, just so I know you're out there, that you've heard me, and we're done. All right. Doesn't look like there's any urgent questions out there right now for the live audience. I'm still going to be here, so if you do have questions, you can still ping them on the Discord, and I should see it and be able to answer. And with that, I think we're done. So good night. Now I just have to find, there it is.